Hello and welcome to this Optical Communications online course. We will discuss today dispersion in optical fibers. Optical fibers have, in addition to dispersion, other characteristics such as attenuation and nonlinearity. We will take up attenuation sometime later, and nonlinearity we will reserve it at the end of the course. When we talk about dispersion, the most visible aspect of dispersion is that if I take a pulse of light and then launch that pulse of light into the fiber, then as the pulse propagates through the fiber and arrives at a distance, arrive at a later distance at the receiver, the effect of dispersion is to basically broaden the pulse. So you might have started with a pulse whose width is around say 1 nanosecond, but then after propagating through the fiber a certain length and arriving at the receiver, then this pulse would have broadened to say 1.5 nanoseconds. So this is the visible aspect of dispersion, and the reasons for such pulse spreading, which is the effect of dispersion, is many. Okay. If you consider the multimode fibers as we have seen can support multiple modes. They can support the fundamental HE11 mode as well as the next higher order modes, right, or the fundamental LP01 mode and the next higher order modes LP11, LP21 and so on. So when you launch a pulse, the pulse energy goes into all these modes. Okay. All these modes are excited and they all begin to travel towards the receiver. What happens is that as these pulse energy in these different modes start to propagate along the fiber, right, they will propagate so with a different velocity. Even if you have launched a simple sinusoidal signal, this sinusoidal signal will travel at a different velocity through the fiber when it is connected to the different modes, that is different modes propagate at different velocities. Therefore, when these different modes arrive at the receiver, right, slightly delayed with respect to each other, because the overall pulse energy will be magnitude of the sum of electric field square. So, you have to consider the electric field coming in from the different modes and then form a coherent sum, take the magnitude square of that one in order to form the intensity or the optical power being proportional to magnitude of E square. So, when you take this square, what you see is that these differently delayed components interact with each other or interfere with each other, so as to give you an effective increase in the pulse. So, this is the pulse spreading that is caused by having different modes propagate at different velocities, and this is a phenomenon which is mainly seen in multimode fibers. It is in fact the phenomenon that is seen in multimode fibers, and that is something that limits the amount of bandwidth that one can or the data rate at which one can communicate with the multimode fiber. If you remember our geometric optics point of view, we talked about a ray of light going or launched inside the core, hitting the cladding, then propagating through the fiber in a zigzag way. However, at different angles corresponding to the angles greater than the critical angle, different angles denote different modes. So, we calculated what happens to the extreme case. You had one ray which is propagating directly along the axis and one ray which was propagating at the critical angle, and then we found that the one which is propagating here would take larger time compared to the one that is propagating centrally, and results in a time delay difference, which in turn gives you the spreading of the pulse. So, this intermodal dispersion is the main characteristic in a multimode fiber. However, when you go to single mode fiber, this problem of intermodal dispersion simply disappears. The reason being, this is a single mode fiber, which means that there is only one mode in which the energy can propagate. This would be the LP01 mode or the LP10 mode, the X and Y modes. So, they will propagate through the fiber, and therefore, there is no problem with multiple modes sharing the energy and hence getting some kind of a interference happening and the pulse spreading happening. So, in the sense that multi modes have disappeared, there is only one mode. So, you do not really expect multi mode dispersion there. However, even single mode fibers exhibit a kind of a dispersion which is very important for long distance optical communications. Okay. This dispersion is called as chromatic dispersion, and it arises simply because beta is a complicated function of frequency, right. Beta is a complicated function of frequency. If you remember, we talked about this normalized propagation constant B, which we defined as beta over k0 square minus n2 square divided by n1 square minus n2 square, right. and then we plotted what happens to this B as a function of the normalized frequency V, right. The V number in fact is inversely proportional to lambda, or it is directly proportional to frequency or omega. Okay. So, this V is a parameter you can think of as V changes, F changes, okay. And we see that beta is not a linear function, but rather for the fundamental mode it goes like this, for the next higher order mode it goes like this, and then it goes in this particular fashion. So, there is actually a non-linear relationship between B and V, since B is for fixed N2, fixed N1 and fixed N2, B is directly giving you the value of beta. Similarly, if you fix all the parameters, the numerical aperture and the radius, this V is giving you how your frequency is changing, or as frequency changes, V changes. So, what we have is a nonlinear relationship between beta and F, and this in turn causes the dispersion, something that we are going to study in the later half of the module, okay, latter half of the module. Now, this dispersion is purely a geometric effect. I can tailor this dispersion by changing the value of beta versus F, and how can I do that? I can change the values of N1, I can change the values of N2, I can change the core area, I can change all these parameters in order to play around and then change the dispersion. For this reason, this is sometimes called as the waveguide dispersion. Okay. So, waveguide dispersion is the geometric dependent dispersion. This dispersion characteristic is because of the circular nature of the optical fiber. If I were to fabricate a rectangular optical fiber, then the corresponding beta versus V will be different. Okay. So, this is the pure geometric effect, or the fact that you are trying to guide in a particular geometry is called as the waveguide dispersion. Okay. Now, in addition to this waveguide dispersion, in every fiber that you consider, there is an extra dispersion called as material dispersion. Material dispersion results because the refractive index becomes a function of lambda, or equivalently the refractive index becomes a function of omega frequency. Okay. Because we fill up with an optical fiber with silicon material, and then we also fill that along with silica we fill some dopants in order to change the refractive index of the core as well as the cladding, and these different particles which are there, they would respond differently to the electric fields that are applied. GeO2, a germanium oxide component, would respond differently corresponding to a silica component, and when you fill up a certain material with this, there will be difference in the material responses to the electric fields, giving rise to a refractive index dependence on the frequency itself, and this frequency dependent refractive index turns out to be the reason for material dispersion. Okay. So, this is simply saying that refractive index is changing, and this change is a function of frequency. Okay. Finally, there is important dispersion source which is called as the polarization mode dispersion. This occurs mainly in the single mode fiber, or at least it is very prominent in the standard single mode fiber, where the two fundamental modes, that is LP01X and LP10Y, that is X polarized and Y polarized waves, the linearly polarized waves, are propagating with their own propagation constants beta x, beta y, which are not equal. Even though if you launch the wave at the same frequency for both the x and y polarized modes, their propagation constants, they will be different, and this difference in the propagation constant eventually gives rise to dispersion. Okay. So, these are the major sources of dispersion in an optical fiber, and we will consider material dispersion in the later class, not really important at this point. We will consider waveguide dispersion and then model both these dispersions by considering beta as a function of frequency. Okay. Because I know that beta is given by omega n by c. So, for any frequency, beta, at least in the free space, is given by omega n by c. Okay. So, in this particular case, if you now look at the ratio of omega by beta from your undergraduate electromagnetic classes, you know that this ratio of omega by beta is called as the phase velocity, right. So, for the free space case, where n is independent of frequency, c being the speed of light is independent of frequency, and omega being the frequency itself, for the free space condition, this phase velocity will be equal to c. Okay. assuming that you are looking, sorry, the phase velocity will be equal to n by c. Okay. Assuming that n is independent of c, then all frequency components will have the same phase velocity. Suppose I consider frequency component omega n, I have an amplitude of this frequency component as say E of omega n. Let me write down the time dependent term as well. So, this is the pulse which I am launching at z equal to 0. Okay. When you launch this one, so this is at z equal to 0, and after propagating a length of z, okay, this is the length of propagation z equal to L, the frequency component arrives here with a phase shift omega nt minus beta of omega n into L. Okay. However, what is beta of omega n? Beta of omega n is the function of beta for a given value of omega n, and this is simply given by omega n into n by c. This omega n is the nth frequency component that I am considering, some frequency component. So, if you rewrite the electric field that you are seeing at the output, it turns out to be e of omega n. This is the amplitude of the electric field at the frequency omega n. You have e power j omega n t minus omega n into z by c, right. So, this is what you get. You can remove e power j omega n outside. So, I can remove this omega n from common factor in this numerator. So, what I get is t minus z by Vph, where Vph is the phase velocity. Now, you might object to this analysis and say, well, I am not going to send only one electric field omega n. So, if you look at its frequency spectrum, right. So, in terms of the frequency spectrum, you will see that this particular sinusoidal signal will have an amplitude of E of omega n, and it is present only at omega equal to omega n. This is a single frequency component, but we know that we are not going to send single frequency components through the fiber. We want to send a pulse through the fiber, and a pulse will have a certain frequency spectrum. So, if this is the time behavior, then taking the Fourier transform will give you the frequency domain picture of this one, f or omega equivalently. So, there is actually a spread of frequencies around it, right. So, that way, instead of talking about a single frequency component, what I can do is I can talk about E of omega, right. I can sum up all these different frequency components. Summing up a group of frequencies in the limit is equivalent of integrating the whole thing. So, integral of E of omega e power j omega t, clearly this is an integration that I am doing is actually meaning that I take many components whose amplitudes can be some E of omega n, right, and then I am multiplying this by e power j omega n t. So, this is essentially many frequency components. So, you go to the frequency domain picture, these are all the different frequency components, each having an amplitude. So, this nth frequency component has an amplitude of E of omega n, this fellow has an amplitude of E of omega n plus 1, and so on. So, if you sum all this, you get this equation, which is what you are launching in the fiber. Okay. So, this expression captures the pulse that is being launched into the fiber at z equal to 0. At z equal to L, each frequency component would arrive at a certain phase velocity or a certain phase delay, but luckily for us the phase delay is independent of frequency. So, all these frequency components are arriving at the same phase delay, right. So, this is very critical. Please remember this step that we have just executed. What we are saying is that you have a particular frequency component, this frequency component propagates through the fiber, okay, and when it propagates a length L through the fiber and arrives at the fiber, what it happens, what the time it takes here to arrive would be some L by phase velocity, and because this phase velocity is independent for all the frequency components, all the frequency components of the input signal arrive at the same time. Okay. All frequency components arrive at the same time. So, at z equal to L, this I should of course write this one as e power j omega t minus L by Vph, and this L by Vph is the total time taken by the frequency component omega in arriving at the receiver. So, you can multiply this one by E of omega, this integral still remains the same. Integration, if you see integration, think of this as summation. Okay. So, this is what you get. Now, if you want, you can take the Fourier inverse transform out of this. So, sorry, we have to also multiply this one by d of omega. I am representing this in the Fourier transform domain, right. But you look at this e power minus j omega L by Vph, right. So, this is just like a phase for me, right, and if you look at this particular thing is simply a constant, right. I can redefine. So, what I want to say here is that I can take this t minus L by Vph and call this as tau, and I get this e power e of omega e power j omega tau d omega, right, and this tau being independent of the frequency, right, is just a constant as far as this integration is concerned, because this integration is going over omega. So, as far as this integral is concerned, this tau is a constant and this is a dummy variable. So, you can see that the Fourier transform of this one will give you the pulse in the time domain with e of tau, but e of tau is nothing but e of t minus L by Vph, right. So, go back to your signals and systems theory and then see that if this is your e of t, so this is t and this is your time domain function e of t, then the function e of t minus L by Vph is simply the same pulse completely unchanged, except that this is delayed by a factor of L by Vph. So, this is the amount of delay tau that you are looking at. This delay incidentally is called as the phase delay tau p. Okay. The important point to note here is that as long as the phase velocity is independent of the frequency, right, the pulse does not get distorted, it does not spread, it simply arrives after a certain time, which is okay. I mean, you have sent a pulse now, after 1 microsecond or 2 microsecond the pulse would arrive at the receiver. It is not a big deal for you. As long as the pulse has not spread out, the pulse has not distorted, it will simply arrive after a delay, and this miracle happens only when the phase velocity is independent of frequency. However, when you consider material dispersion, this phase velocity will not be independent of frequency. Rather, what happens is that because your n will be a function of omega now, n is a function of frequency or n is a function of wavelength, because of this one you will see that phase velocity is now given by n of omega by c, right, assuming that c is the speed of light is a constant, this is what you get, and your beta of omega, the propagation constant for any given frequency omega, is given by omega into n of omega by c. Clearly this propagation constant will be different because for different values of omega the value of n will be different. Okay. So, because of this reason what you now see is that energy does not really propagate at the phase velocity, but rather energy propagates at what is called as the group velocity. So, whenever you talk of a pulse or an envelope, especially the one that is modulated by a carrier frequency, when it propagates then the carrier will arrive. So, this is your carrier. When you modulate a carrier you might be generating a modulated pulse. Okay. So, you might be generating a pulse like this is the envelope of the pulse which is propagating. So, I should probably write it like this. So, when this pulse is launched into the fiber, it propagates through the fiber of a certain length L, then the carrier would arrive at a delay of tau p, whereas the envelope would arrive at a delay of tau g, which is called as the group delay. Okay, and this group delay is a function of group velocity Vg. Okay, and Vg is defined as d omega by d beta. What is the group velocity for the case of free space propagation or the propagation that we saw in the previous 10 minutes? In previously what we saw was beta was given by omega n by c, and n was independent of frequency, correct. And if you evaluate this d omega by d beta, which is nothing but 1 by d beta by d omega, correct, just interchanging this equation or rewriting that equation, but beta is omega n by c. So, d beta by d omega will be equal to n by c, right. So, 1 by n by c is nothing but c by n, which is simply equal to the phase velocity of the medium. So, in the case when beta is equal to omega n by c and n is independent of the frequency, c is just the speed of light, then group velocity Vg will be equal to phase velocity, and this is the reason why the envelope also arrives at the same time. So, group delay and time delay are equal. However, in material dispersion case, beta is a function of frequency right. It is given by omega into n of omega by c. This n of omega depends on the material constants and this is not independent of frequency. So, if you now try to take this d beta by d omega, what you get here is 1 by c is a constant, I can pull this out, you get omega dn by d omega plus n of omega, right. So, you see here that this d beta by d omega is actually given by 1 by group velocity, correct. So, group velocity is d omega by d beta, but 1 by group velocity is this one. So, you can see here that this can be written as some term divided by c, right. For the phase velocity we had some refractive index n, or rather 1 by phase velocity we had n by c here. Similarly, here you have some number divided by c for 1 by Vg, or equivalently for Vg equal to c by this term. This term is nothing but omega dn by d omega plus n of omega. Okay. This term is what is normally called as the group index Ng. So, you get Vg as c by Ng, where Ng is the group index. Okay. The group index is a function of frequency because n is a function of frequency. You can actually talk in terms of the wavelength here, you can convert these relationships into wavelength relationship, assuming that n is a function of lambda, that is represent n as a function of lambda rather than representing this one as a function of frequency. Then you can show that if you take lambda is equal to 2 pi c by omega, is that correct? Because omega is 2 pi into f, c by f is lambda. So, you get lambda here, which is the free space wavelength. So, maybe we just write this one as lambda 0. So, lambda 0 is the free space wavelength, okay, given by this expression. Now, if you were to differentiate this one, I know that lambda is given by c by f or 2 pi c by omega, anyway this is the same this one. So, now if I differentiate this lambda with respect to omega, okay, I can do this. What do I get? I get here as 2 pi c is a constant. What is 1 d by d omega of 1 by omega? It is omega into 0 minus 1 divided by omega square. You get here as 2 pi c by omega square, okay. But what you want is dn by d omega, but dn by d omega can be written as dn by d lambda times d lambda by d omega, correct. So, this d lambda will cancel with each other. Therefore, I can write this one as dn by d lambda. I already know what is d lambda by d omega. D lambda by d omega is nothing but minus 2 pi c by omega square, but in the group index or the group index here Ng is given by omega into dn by d omega plus n of omega. This omega into dn by d omega can be obtained because dn by d omega is this fellow which we have just calculated. Multiplying this one by omega will cancel out an omega here. So, what you get is minus 2 pi c by omega dn by d lambda plus n of omega. Rather than n of omega, we can call this as n of lambda because that is what we have said that, right. So, n can be considered as a function of omega or it can be considered as a function of lambda, and 2 pi c by omega is nothing but lambda 0. Therefore, this is minus lambda 0 dn by d lambda 0, sorry, this has to be lambda 0 because we had considered this as the free space wavelength plus n of lambda. This is the group index Ng. Equivalently, I can rearrange the terms and then write this as n of lambda 0 minus lambda 0 dn by d lambda 0. Okay. So, as long as the refractive index is changing with respect to wavelength, you have a group velocity which is dependent on lambda, and this change in group velocity which is dependent on the particular lambda that is propagating through the fiber is causes material dispersion and causes pulse spreading. Okay. The other dispersion that happens is the chromatic dispersion. So, here you have beta as a function of frequency omega, and this is purely because you have a waveguide structure, and this equation for beta of omega is not very easy to find out, because what it requires you to do is to find first for a given frequency omega what is the corresponding propagation constant beta of omega. However, remember, how do I calculate beta of omega for a single mode fiber? I have to go back and write that big complicated equation, right. In the last 2 modules we have seen in discussing the modes of an optical fiber, how do I obtain the propagation constant beta? I have to first express W in terms of U, find out what is U, from U I have to find out beta, right. So, that is the long procedure which I have to follow with this big equation that we wrote down, some J nu plus K nu into K1 square, that equation that we wrote down, or even if it is simplified version of the weakly guided approximation, calculating value of beta as a function of omega is a tricky and numerically oriented problem. Luckily for us, people have solved it earlier, and the results are this equation which we wrote down slightly earlier in the module today, right. So, this gives you beta as a function of omega. If you would like, you can also make beta as a function of lambda. Okay. So, instead of talking about beta as a function of omega, you can talk about beta as a function of lambda, and you will be able to obtain through numerical methods how this beta actually varies with respect to omega. And because beta is not a straight line, the derivative of beta with respect to omega, which will give you 1 by group velocity, will not be a constant term, I meant to say that, right, because beta is nonlinear function of omega. Okay. Now, regardless of what kind of dispersion that we are considering, what seems to be clear is that I can consider beta as a function of frequency omega or equivalently in terms of lambda, and if I consider a modulated spectrum, right. So, I consider a carrier at say omega 0, and there is a modulated spectrum around that whose width, call this as delta omega, is much smaller than corresponding to the center frequency or the carrier frequency omega 0. So, this is in the frequency domain. If you look at this in the time domain, you might actually see a time dependent or a time waveform here. The objective for us would be to try and find what happens to this pulse when you have non-zero dispersion in the fiber, and that is what we are going to do in the next module. Thank you very much.